Both Oggy and Fatima came to see me yesterday, separately, but about the same issue. They'd been reading their notes, as all of you do, of course, and were confused a bit by the term electrolyte. So I told them I'd try to clarify that today. The term electrolytes, I want to make this clear right from the start. We're talking, this word is in reference to solutes, things that we dissolve in solvents to make a solution. And I'll only be talking about solutions in which the solvent is water. So it's a class of substances. The name is not all that the name is very significant only in the sense that that it has a meaning. When we use this, like any other language, dog or giraffe or toaster, we know what we're talking about. It's the meaning of the term, what it is referring to, that is important. So we're talking about a class of solutes. Solutes could be such that they turn a solution blue or yellow, different classes. They could be another class of distinction, is that the solution in which you dissolve a solute could then become an oxidizing agent or a reducing agent. Or another distinction, the solution that they dissolve in could be an acidic solution or an alkaline solution. Just a whole range of ways in which we can distinguish based upon some criteria. And electrolytes have another criteria. Now the word electrolyte, can you think by reference to any other words, do a sort of a word association test, what do you think it might be related to? Yasmina? Electricity. Excellent. Everything that we're going to do today is concerned with the passage of electricity. And Daniel? Yeah, a drink that athletes have when they've been working very hard, called electrolytes, referred to as electrolytes. And I've got a bit of a warning. I'll come back and talk about a bit of loose language there. Yeah. And even electrons. Okay, you might well expect that there's a link here between electrolytes and electrons. But in the context of we're talking about today, absolutely not electrons. We'll come back to there in a second. Firstly, I want to show you something. I have here a little apparatus. I've got an apparatus with two electrodes, and I've turned this on, and there's now an electric potential, DC potential, between these two plates or electrodes. Don't worry, there's a transformer here, and it's a very low voltage DC potential or supply, so I'm not going to kill myself. If electricity can flow between those two plates, and it does flow between those two plates, this light will come on. So you're already thinking air is there. Air is not letting the electricity flow. It is not conducting electricity. This is some pure water, deionized, distilled water. Let's see what happens when we put this into here. Nothing, all right? Water is a non-conductor of electricity. And now, some ordinary household salt, sodium chloride. Put some of this into here. And give it a stir. And what do you think? You're guessing I'm leading you up to something? Wow. The presence of salt dissolved in that solution means that electricity flows between those two electrodes. And you're asking, why? How come? Why does salt make this solution conduct electricity? Without the salt, it doesn't. It's an insulator. I'm going to first of all tell you that all all forms of electricity are the flow of charged species. In an electric cable, like this, the flow of electricity is by electrons moving along. And the reason I gave you a caution before is that in this solution, it is not electrons that are moving. So what can it be? Well, we've talked about the dissolving of ionic solids before, and I guess I'm now talking particularly about ionic substances, salts, ionic solids. In the case of sodium chloride, we can represent in a very oversimplified form sodium ions, chloride ions, sodium ions, chloride ions, sodium ions. In the solid, chloride ions, masses and masses of these held together in a lattice, not allowed to move with respect to each other because everyone is hanging on to a few around it. We put it into water and along come some water molecules with their positive ends pointing towards the chloride ions and some negative ends pointing towards the sodium ions. And the forces of attraction are such that they can rip the ions apart, separate the ions so that they go into solution as independent of each other sodium ions surrounded by water molecules hanging onto them with the negative oxygen in, and chloride ions, chloride ions, and sodium ions, water molecules. And now we've got a reasonable explanation of why electricity is flowing in this solution, and that is that depending which way this potential is going, it might be we've got these things are free to move because they've got a charge and electric potential will force them in one direction. The positive ones, let's say, that way, and the negative ones that way, and the movement of charged species is electricity. So this is in fact evidence of what happens when we put sodium chloride into water. It is one of those things which, when we put it into water, the solution conducts electricity. That's what electrolyte is. It's a solute which, when dissolved in, we could talk about any solvent. I'm specifically talking about water solutions, aqueous solutions today. So in this case, electrolytes are substances called solutes which, when we put them into water, form a solution which conducts electricity. And our rationale for why it conducts electricity is that the ions separate and they move in particular directions. The movement of the charged species is electricity. Now what about covalent molecular substances? Molecular. Is that right? I think so. Substances when they are used as solvents. Well, I've got a little bit more to show you. I'll turn this off. I'll wash this down. And get another beaker of pure water. Turn it on. Pure water as we saw before. Nothing. What about if we add some sugar? Sitting a molecule C12H22O11. We can do that pretty easily. I have some table sugar, white sugar. Pretty pure, very, very pure. And we can get some of this. Salt causes a solution to conduct electricity. Does sugar. Put it in. Stir it around. And it doesn't. Let's try another molecular compound. Something that consists of molecules. Ethanol. Consisting of molecules, C2H5OH. We won't worry about what the molecular structure is for now. I've got some ethanol in the form of methylated spirits, 95 point something % of ethanol with a bit of methanol in it. So if you go to a hardware store and buy some of this and drink it, the methanol will at least blind you, if not kill you. It's designed to discourage you from drinking it. There's a fair bit in there. And nothing. Well, you're always hypothesizing, aren't you, in your mind? Provisional hypotheses. And you're probably saying, no, well, these things consist of molecules and there's no ions. So why would it conduct electricity? And that's excellent thinking. However, if you go to generalize and overgeneralize, ionic compounds, electrolytes, covalent molecular substance, and non-electrolytes, we can get into a bit of trouble. These ones are non-electrolytes. In a sense, on this criterion, the opposite of things which are electrolytes. Now, when we can rationalise that on grounds that when these things dissolve in water, they don't separate into any sort of ions. There are only uncharged molecular species there, and they don't carry a current. But be careful about taking that too far. It's a bit like once upon a time, 230, 40 years ago, people from Europe presumed that swans were white until they came to Fremantle. Whoops. And we might have an oops experience here. I'm foreshadowing. I've got some acetic acid. It's already dissolved in water, but I'm just going to now make a more dilute solution of acetic acid in water, or ethanoic acid, not sure which name you use. Put some in there. Oh, the smell is overpowering. It's a pretty concentrated solution with that vinegar smell. See that the light has come on, but it's not very bright. But since the light has come on, there is some conduction of electricity going on. Acetic acid is an electrolyte. But the light doesn't come on very brightly. We'll come back to that in a second. Let's try some hydrogen chloride. Hydrogen chloride is a gas. Dissolve it in water. It's very soluble in water. We get a solution that we commonly refer to as hydrochloric acid solution. And if we put some of that into water, I don't think I need to stir it. Wow. That is also an electrolyte. I wonder what we might conclude from the fact that the light is glowing much, much more brightly than in the case of acetic acid. All of these are molecular substances. These ones the solutions of these ones in water don't conduct electricity. The solutions of these ones in water do conduct electricity. Therefore, we give them a name, not squizzy whistles, but electrolytes. Now, how do we rationalise that? The fact that these are electrolytes, let me turn that off, and in particular that this seems to conduct less well than hydrochloric acid solutions of hydrogen chloride gas. Well, the rationalisation that I guess you'll have to accept from me, that molecules of hydrogen chloride, put them into water, these are quite polar. This is sort of unequal sharing of this electron pair here, more towards the chlorine, which makes it partly negative. Then along come the waters, and the negative end of the water. So the hydrogen ion, enough attraction for these two ions that they pull them apart, so that the molecules are ionized. I can get rid of this now. Provide a little bit more blackboard space, and we can represent that as hydrogen chloride in solution forms hydrogen ions with water molecules around them, and chloride ions with water molecules around them, and entirely so. There are no hydrogen chloride molecules in solution. So in fact I've sort of represented there's no such thing as HCl with water molecules around them. They don't exist. This is what we call a strong electrolyte. All of the molecules are ionized. In the case of acetic acid, we have a different explanation. Remember, the light was less bright. So we can maybe deduce that there are less ions. So it carries less current. So the light is less bright. All that sort of makes sense, I hope. So N3COOH in aqueous solution. And now I'm going to use another notation that you've struck before. An arrow that means dynamic chemical equilibrium. And in this particular case, only some of these ionize. Some, and that's what this means. I'll write the equation first. CH3COO minus with water molecules around it, and hydrogen ions with water molecules around them. And now we apply the electric potential, and the negative ions can go one way, and the hydrogen ions go the other way. But there aren't so many. In a solution of acetic acid, which is about 0.1 molar, only about 1% of these do that, and 99% stay as that. We call that a weak electrolyte. Okay, so we have electrolytes and non-electrolytes, and in the molecular substances, some are non-electrolytes, some are electrolytes, and of the electrolytes, some are strong electrolytes, some are weak electrolytes, and we'll talk about that more and more and more. You could write a Venn diagram, draw a Venn diagram about the relationships between these things. So we'll talk about that tomorrow and clarify the difference between weak and strong electrolytes, which are molecular solutes. Just a bit of some 2 or 3 points. Does water conduct electricity? Well, I just showed you that pure water does not. But if there were some fallen electric power lines on the ground and there was water there, maybe there's been flow in a flood coming down to form a pool. Maybe there's water coming out of a pipe. In both of those cases, there's a very high chance that they contain ions. And those ions would render that puddle of water the ability to conduct electricity. Don't stand in it and try to do something clever. Right? What we might call water in the practical sense is a solution of stuff in water very often. Just a reminder, flowing through this cable are negatively charged electrons. In solution, no electrons flow. It's charged species called ions. Positive ions, negative ions, like sodium ions, chloride ions. And just one reference to those electrolyte solutions that people will drink if they've been working fairly hard. People will say, I'm going to drink some electrolyte. Now, don't argue with them, but you know that electrolytes are solutes. It's the stuff that's dissolved in solution. So an electrolyte solution, aid, contains maybe magnesium ions, sulfate ions, potassium ions, chloride ions, stuff like that. You can think to yourself, yeah, you can call it electrolyte, but I know that the stuff dissolved in them